recording. So let's go back to it. So last time we started talking about numerical linear algebra. And with numerical linear algebra, we already talked about Krylov spaces, right? Subspaces. So this is the main goal of the presentation, to talk about systems of equation as we did last time. And now we'll dive deeper into what we call Arnoldi vectors and eigenvalues. And I'll show you how to do this computation, okay? So I'll go a little bit quickly through what we covered last time. So we said when a matrix or a tensor is really large, or big data, we will have often to sample the matrix. So in fact, in this section, we summarize the central ideas of numerical linear algebra. We don't claim that we cover all the ideas. So it may seem impossible, for example, that random sampling would give a reliable answer, but in fact it does. So the aim, for example, is to solve AX equals B, or in general, the eigenvector problem, AX equals lambda X, or the SVD, AB equals sigma V U. So to get a numerical approach for the SVD problem. So our goal is to outline important iterative algorithms for that to solve systems of equations or compute eigenvalues. So first of all, we've shown last time how we can split the matrix A of a linear system into two matrices S and T, such that A equals S minus T. And the linear system AX equals B becomes SX equals TX plus B. And if you start by a given x0, you can, at every iteration, compute the next vector x1 based on the previous vector x0. For example, the next iteration would be to compute x2 that solves the x4 plus 1 equals b. Okay? And of course, we said that if S is well chosen, then the convergence is fast. And S is well chosen when, in fact, the error is reduced at every iteration, because the error, in fact, is multiplied by S minus 1, S inverse times T at every iteration. So you get the norm of S inverse T, which is less than 1, then you can say that you have a fast convergence. So for example, in that case where we have this beautiful linear system 1, 1, 1, 1, 2, 1, 1, 0, 1, and this 3, 2, 4 right-hand side, I intentionally chose S to be just a diagonal matrix, and I started from x0 equal 1, 1, 1. And with these Python files I'll upload just after the class, even with a magnitude of S inverse times T, which is a little bit higher than 1, we were able to get to converge towards, in fact, the exact solution to our linear system in fact, 10 or 20 iteration, as I remember. Okay? But still, the main difficulty lies here in the right splitting of A into S. So, how to split now? We are going to enlarge the problem, because this even solving the eigenvector problem is, in fact, similar to solving a linear system. In fact, it is a solution to a linear system. So, I'll talk now about what we call Arnoldi vectors and eigenvalues. First of all, the Krylov subspaces, which is an intuitive method for finding the largest, in fact, an absolute value eigenvalue for your m by m matrix. It is based on the concept we call the power iteration. So we start by computing using an arbitrary initial vector b. We compute what we call ab, a squared b, a3b till a n minus 1b. And if you count them all, since you go from 1 to n minus 1, you have a minus 1 vector, you add the initial b, and you have n vectors. And these, they do represent the basis of what we call the Krylov subspace. Okay? The next iteration is to normalize the result after every application of the matrix A. So matrix vector multiplications, in fact, if this matrix application is multiplication is fast, things go well. And this is typically the case when we have a sparse matrix A. Don't forget, the intention is not to compute a square or a 3 or a to the n first, but just to multiply what you obtained in the last iteration by n. And we say that this sequence is in fact converging towards the eigenvector corresponding to the largest eigenvalue of A. And these combinations, the combinations of the n vectors, they do represent in fact the nth Krylov subspace. They make an nth order, an nth dimensional Krylov subspace. So let's talk briefly about the Krylov subspaces. Well, the name is typical, typically, let's say, Russian. And we look inside these subspaces, this subspace, Kn, for a close approximation to the desired solution eigenvector. Okay? Why we are doing this? Because when we deal with huge sized matrices, basically computing eigenvalues is a problem. So what about computing eigenvectors? So we are just mainly interested in the largest chunks of the matrix. So we are interested in computing numerically these largest chunks. The first problem is to find a much better basis than those in the Krylov subspace. Why? Because these vectors in the Krylov subspace, they are not generally orthogonal. And there is a way to generate some of them. What we call is the Q1 to Q1 vectors. And it's based on the Gram-Schmidt idea that if you can subtract out the projections of V, AQ, and xk onto all the earlier vectors q's. So at every iteration, we're going to subtract A times qk. Okay? So what do we expect? We expect the vectors of the spaces to span good approximation of the eigenvectors corresponding to the n largest eigenvectors. So for the same reason that A to the power n minus 1b is supposed to approximate, the last one is supposed to approximate the dominant eigenvector. Okay? So let's see the Arnoldi iteration. So the Arnoldi iteration is a kind of a development of the modified version of the Gram-Schmidt process. The Arnoldi iteration uses a modified Gram-Schmidt process to produce what? A sequence of orthonormal vectors or orthonormal bases for the Krylov subspace. Okay, so our objective is to generate Q1, Q2, Qn vectors which are orthonormal. So they are orthogonal and they have unit vectors. Okay, so for every n, the n vectors, they span the Krylov subspace, so they are a basis for the Krylov subspace. I'll detail here the iteration so we can understand. First of all, in every algorithm, we need an initialization. So we'll start with the first Q, which is just obtained from B divided. This is not B1. This is a miswriting on my part. Sorry for that. Should be B divided by the norm of B. What is B? B is just a general or arbitrary vector you start with. Okay? Of course, you should have a non-zero norm, at least. Otherwise, you cannot proceed. Once you created this this first vector Q1, you are moving to the next vectors. Now the question is how to move on. Of course, now what we're gonna say is that we're gonna enter a first loop on K here. So let me write. You're gonna enter a first loop on K. So this is our loop. Okay? And at the beginning of the loop, I'm gonna generate Q and xk, which is equal to A times Qk minus 1. So basically, this is like imitating the way we generated the vectors in the Krylov subspace. Am I right? Because every time you multiply by A. Am I right? You got it? Okay, now that you entered, you have to make them orthogonal. So how to make it orthogonal? So we try to compute the inner product from J equals 1, because the new vector you generated has to be orthogonal to all the previous one. So you generated a new vector, it has to be orthogonal to all the previous one. So you will go back from 1 to k minus 1. So if you are at 2 with k equals 2, so you have only one preceding vector. So you just need to verify that the new vector you generated is orthogonal to the previous one. I mean, Q2, you verify it with Q1. Q3, you verify it with Q2 and Q1. Am I right? So to do that, you compute the inner product, which is Hj and xk minus 1, because j is the iterator here, and k minus 1 is just where you are going to stop. So you start, j is running from 1 to k minus 1. So it will go from, for example, if k is equal to 4, j goes from 1 to 3. You compute the inner product, okay? And since you need this inner product at the end to be equal to 0, you're going to subtract the projection. So from qk, you're going to subtract this value, okay? You subtract the inner product. Now you compute the norm, which the new value we call hk plus 1 over k, which is called qk. So this qk you obtain it when you update it. It's exactly the same qk you obtained first, minus the inner product of qk by qj. Okay? You compute the norm of the new vector you obtained. Hello? And you can say now the new vector you generate is what you call qk plus 1, which is qk divided by its norm, has a norm 1. And automatically, every time you will update, you will end up with orthonormal vectors. So they are orthogonals because you just made sure that you subtracted the remaining part, which is the dot product. Okay? And next, they have unit norm. Okay? So this is the base idea of the Arnoldi algorithm. So just to give you again some insights, you have two main loops here, a loop on k and a loop on j, which runs on all the previous vectors you generate. Okay? So to generate a new vector, you don't need only to multiply qk minus 1 by a, but you need to update it in a way that it generates a new vector which is orthogonal and has a unit norm. The j loop, in fact, what happens, the j loop projects out the components of qk in the directions of all the preceding vectors, q1 to qk minus 1, which when you do this projection, what you are doing, you ensure orthogonality of the generated thing. So remember, guys, basic concept we see in Math405, if you have two vectors, u and v, how do we obtain, if I'm saying, like, I'm looking for the projection of v over u, how do I do projection of v over u? I write it like this usually, right? If you remember Math405, guys, you've taken Math405? Sah? Yes, Abrazim. So remember, to obtain the projection, which is this part, we do u dot v, the dot product, divided by just what? The norm of u. And this is exactly what we are doing. So when you do the dot product and you divide by the norm here, the norm divided by the norm of q, so remember, if I do this, we'll obtain a projection. So this is what I'm saying the last item. Okay? Okay? So these are the main idea. I believe here and now I build the foundation for your understanding. Okay? It's like when you try to build a house, knowledge is like this. You have to get the foundations ready. If you don't have the foundations ready, you cannot build your own walls. So the goal of the teacher is to put these foundations. Okay? If you don't have these foundations, it cannot work. Now it's up to you to understand the remaining parts, the missing part, the missing bricks in your walls. Okay? So since I detailed how things are rolling, now let me talk about the matrix formulation. Or you want to go switch to the programming part. It's up to you guys.
Programming parts.
Okay, so I'll switch. Be my guest. I'll switch to the programming part now. For the programming part, I need to share with you my programming screen, my programming application. Okay, so what I'm happy to share with you is that this now is going to be like the most advanced algorithm we see. Okay. Last time, what I've shown you was a development where we kind of solved this 2x2 linear system, if you remember. Okay. So that was the first way I've shown you how to iterate, in fact, to implement a small algorithm that runs and gives you the solution of a small linear system. Here it was a 2x2. Here it was a 3x3. Okay. Well, now I have this file, which is called the Arnoldi algorithm. Well, I re-implement, okay, what has been said in the slides. Okay. So let's go through it. So first of all, I'm pretty sure you did at least one C programming or C++ programming course. Am I right?
Yeah.
All hands are raised, mashallah. Even those who are quiet, they did. Okay. So, of course, you know then what is a function. So here we are defining a function, we call it Arnoldi Iteration. And it takes as arguments a, b, and n. And that's all we need. Okay? A, b, and n. Type. And what do you mean? You mean the size of the Krylov subspace you want to generate. Okay? So what is the goal of the Arnoldi iteration? Here is to compute a basis of the n+1 Krylov subspace of A. And the space is spanned by b till a to the power n b. So basically here, when you go here and give n, you're going to have an n+1 subspace. In our presentation, we are obtaining, we stop at n to the power -1. Just a small difference in the incrementation or in the variety. So the arguments, first of all, you have a square array matrix, m by m, b, an initial vector of your choice of length m, and n is the dimension of the Krylov space, and must be larger than 1, of course. And what it returns is your Q array. The Q contains all the vectors Q1 till Qn, the basis of your the orthonormal basis of the Krylov space. And we have also what we call an upper Hessenberg matrix. Okay, I'll go back to it and explain what is an Hessenberg matrix. In fact, in the slide, these HJK plus 1 we obtained, they're part, in fact, what we call the Hessenberg matrix. Okay, it has nothing to do with my family name, unfortunately. So first of all, I'm detailing just my code before running. I'm printing A in my function, just make sure that things are read and passed to the function correctly. And I'm using now more advanced functions in Python. When I do a.shape0, I'm taken from A the size of it. So this returns the size of A. Okay? And then I'm creating what I'm creating is an H matrix, the Hessenberg matrix. I'm filling it with 0, but I'm giving the size here, n+1 by n. So when I say zeros, it means it is initialized to zeros right now, okay? And I'm creating this Q matrix, capital Q, which will contain the Q vectors, the Q1 till Qn vectors, and its size is going to be m+1, okay? Now I'm computing, since I gave B, I passed B to the matrix, I'm computing the first vector Q, which I called Q1 in my slides. It's B divided by the norm of B. Okay, so we normalize the first input vector. I'm printing it out, okay, and I'm inserting it in Q. So I'm inserting it in transpose, because here, when it's computed, here is going to be a line vector, but I want to see it as a column vector in Q. Okay, so I just need to be careful here. Type. So before now, I print Q, make sure that everything is passed carefully. Now I'm going to enter the first K loop I define. The first K loop, what I'm going to do, I'm computing V, which is A times Q. k. So I'm going to compute qk plus 1 in fact. Okay? So, or qk if I'm having qk minus 1 in my hands. So we generate here a new candidate vector. And I'm ready to enter now the J loop. I print it out just for you guys. Now, the goal of the function is that it's supposed to summarize the work. So the printing out is just for own user to understand what's going on, or for the programmer to understand what's going on. But the main goal is to make all these things hidden. This is kind of the work of debugging, to understand deeper what's going on. But now we will comment it. We'll comment all the printouts when we run things. So for J now, we're going from, say, we said from 1 to K. Right? Here I'm stopping, I'm running from 0 to K. So it will stop at K. I'm giving the range till K plus 1. Okay? I will generate the dot product, which is the product of the vector in position J in Q by our new vector V, the new candidate vector. Okay? So this is done here. Sorry, this keeps on appearing, and I don't know why. And I'll print HJ, and I'll do what? I'll subtract the dot product HJK by Q from the V transpose I just obtained. Okay? So since I had V at the beginning, now I computed the dot product, and I'll subtract the dot product from V. I have a temporary variable I'm calling temp, and to me V, I want to see it in a color. So I'll transpose it. Okay? So V is just the temp of the transpose of the temp. So I obtain V now, and I will write down now what is the entry in the asymptotic matrix, which is a H with index k plus 1k. So it's going to be in the k plus 1th row, kth column of H, and I'm going to use just the normal V. Here I'm defining epsilon to be 1 times 10 to the power minus 12, which means this is the kind of precision parameter I'm using for my computation. And I'm making sure now that if this is not equal to 0, so if it's greater than epsilon, if this H here is larger than epsilon, then I can divide by it. So I'm making sure that I don't have a segregation fault. I don't have running error when I'm running my algorithm. I'm not dividing by 0, okay? Because in the subcode or in the pseudocode, we were dividing by this norm. I'm making sure that the norm is not 0. So if the norm is not 0, Q, the new candidate vector, is just equal to V divided by the norm of V, okay? The 0 vector is the 0 vector. What I mean, the 0 vector is produced. I mean the orthonormal vector is produced. Okay, and now just I need to insert it in my big matrix Q and update. Okay. Finally, at the end, of course, I'm giving an else to my if here, in case the norm is equal to 0. Of course, I'm stopping my iteration. I cannot proceed from there. Okay, so else we can return when we stop the loop. So if I'm stopping, I will return Q and H. Otherwise, if I reach the end of my two K and J loops, I can return the two matrices Q and H. Okay, when you go back to your things after the exam, and you, inshallah, you'll dive in a little bit deeper in the Arnoldi algorithm, you'll have time to understand it. Now, all what I have to say is that I'm giving you an example where I have a huge matrix. So, for example, here in my matrix, what do I have? I kind of have a 10 by 10 matrix. Okay? See, this is just one of the rows of A. You see it, guys? Are you still with me? This is a 10 by 10 matrix. And of course, if I'm talking about 10 by 10 matrix, so it's going to be a headache to find the eigenvalues and eigenvectors. So I'm going to use Arnoldi's algorithm to do this. I'm going to use Arnoldi's iteration to do this. Okay, so I'm passing this matrix 10 by 10. I'm just giving a a vector B, and I'm calling my function here, just saying take Arnoldi iteration for AB and just giving n equals 9. Okay, so I can obtain a beautiful matrix here, and then I'll just do comparing my results. So I'll first of all I'll save this just to be able to run my my project. So I'll save it as my main source file, and I'll run it. Hopefully it is going to work, not crash. And last time I verified this was working well. And remember, we entered the 10 by 10 matrix. Huh? We are not talking anymore about small matrices. Okay, it's working. Beautiful. What's going on? Let's see what happened. Okay, so let's see what happened. So remember, first of all, let's go back. So this is our matrix A. See, it's a 10 by 10 matrix. So now this is the matrix that has been passed to the function. This is my initial vector that was computed, which is equal to B divided by the norm of B. Okay, so this is what is going to be used. And now, what happened before entering the two loops, I inserted this vector Q in our big matrix Q. So this is my initial vector Q, let's say Q1. Okay, and now I'm starting this iteration. So I'm saying for k equals 0. So now I'm in the k loop. What I'm doing, I'm computing the first A times Q. So A times Q1, first of all. This is A times Q1. So if I compute A times Q1, I will produce what? First of all, the dot product, the new vector Q, which is here, V, multiplied by the previous one, Q1. Okay? And I'll subtract the dot product, I'll subtract it from Q2 itself, and I'll divide by the norm. So I see that the first HJK I obtained is here. And the first Q I obtained is here. Okay? Right. You see this idea about the 19.2 Shabab? So I'm having to, how many iterations? I said I'm going to have at least 10 since I gave n equals 10. Okay? So I'm proceeding. I'm not going to dive into details. So at the end, I'm going to display Q and H. Okay? This is what I want to show you at the end, how to display Q and H. Okay, now I have reached Q equals K equals 8. Okay, I'm just displaying. All of this should not have been seen, Shabab. Okay. Well, this is my last thing. So this is the matrix. This beautiful matrix contains all the vectors Q1 till Qn. Okay, and since I said n equals 9, so it's basically giving me how many vectors? N plus 1, 10 vectors. You see why I've chosen n equals 9? Because it's going to give me 10 vectors for my 10 by 10 matrix. Okay, now, but in general, remember, we have an m by m matrix, so your matrix could be 100 by 100. And you want to work on a reduced dimension set. So the Krylov space is supposed to be with much lower dimension. Now that you generated Q, I generated also a Heisenberg matrix, which contains all these things. And let's check the details. What does this mean, the 19.2? In fact, this 19.2, as you see, it's very large compared to all the values around it. What do you think it represents, Shuda? The first HJK I've shown you, because I've shown you the first iteration. What do you think it means?
Maybe the first eigenvalue?
The most important eigenvalue. Guess what? Thank you very much, Abdulaziz. So you see that now that I absorbed this in mind, let's say this is an approximation for the eigenvalue, the largest eigenvalue of A. And in fact, if I go to the this, I'm displaying the singular vector decomposition, but I want to show you something. Where is my eigenvalue? The U, V. Where can I forgot? Where are my eigenvalues? Because I was displaying them. Did I display them? I don't think I did. No, I didn't. Okay. So let me display the eigenvalues again, so you can see them. Okay. So no, I did. This is it. Should be in the use. Okay. So sorry again. I'll run it again. So in fact, this 19.2 is just an estimation for the largest eigenvalue, which means that in fact the algorithm did the job. So it's going to run again. Sorry for that. So I have just 9 iterations. Okay. So what are the eigenvalues, Shabab? So remember when we talked about the eigenvalues, we said that they are ordered generally in descending or increasing order. It is an ascending order. You see the largest eigenvalue is here. It's 20.8. And the estimation we got here is how much? 19.2. Okay? You see it? So our estimation for this largest chunk, you see, compared to all the other guys, it's quite important. Remember, this eigenvalue is going to be very important to give us the singular value decomposition first rank 1 matrix. So basically, analytically, you cannot get it anymore, but we get it numerically. And this is why Arnoldi iteration is important. So you can approximate numerically the best rank 1 or rank K approximation of your matrix. You get my point, guys? So the 19.2 we got at the beginning is an estimation for the 20.8. Yes, Muhammad, go ahead.
I understood the procedure, but when entering the loop, what we are updating, and for the final Q, what does it represent? Since
the final,
yeah,
the final Q. Well, yeah. These are all the Qs here in my Q matrix are the orthonormal bases. They represent the orthonormal base of my Krylov space. You get it?
Yes.
So the first vector I generate, which I've shown you in the iteration, is the eigenvector, which is corresponding to the 9.2 eigenvalue estimate. Okay. The last one is an estimation for the last eigenvector. But again, what we are interested with is not the least one, it's the largest one. So there might be no similarities with the least important eigenvector. But you can see, for example, for the next eigenvalue, which is 4, check it out. It's 4.4, right? Mohammed, are you with me?
Yes, I'm with you, yes.
You see this 4.4, keep an eye on it. If I check the eigenvalues, the next eigenvalue after 20 was 5.3. So it's not that far. You see my point?
Yeah, okay. But is there a way that we didn't use the iteration as we used before? We are using the iteration to produce a new eigenvectors and a new eigenvalues. So we are not updating our original our values, starting values.
Yeah, yeah. Look, Mohammed, there is. Let me. Can I? I understand exactly what you want to say, but let me re-say it so everyone understands. We are not calculating eigenvalues. We are estimating eigenvalues. You get my point?
Yes.
Okay, so this is very important for you to understand. So the goal is not to calculate precisely eigenvalues, to estimate them. Okay? And what is one factor which is very important is that, in fact, I gave a random vector B. So basically here it has an important impact on the way I'm going to converge, right? Because B here is for my own setting. This is the matrix I had before. And this is kind of my first estimation of the first vector. Okay? Of course, if your first estimation is wrong, it's going to be completely messed up. See, because Q1 itself is just V divided by the norm of V. So if your first estimation is wrong, basically, so I'm kind of trying to approach what the most important eigenvector would be. You get my point? Okay, so if you're doing a bad initialization, things are not going to work. Did I answer your question, Mohammed?
Yes, but can you repeat this part? If you start
the iteration.
wrong. Yeah.
So when I start with the iteration, I start with Q equals V divided by the norm of V, and I'm passing it to Q, so it's going to be in my first column of Q. Okay? Then I'll start generating new vectors. So here I enter the K loop. K basically will run from 1 to N. So to me, N is 9 now in my call. So I compute the first vector V, so the new candidate, which is A times Q. So basically, I'm doing what Krylov is saying. Okay? So iteration after iteration in the K loop, I'm doing A squared K, A squared Q, A3Q, A4Q, till I reach N minus 1. Got my point? Now, since I produced the new vector V, I'm going to make sure that I compute the dot product, V times Q, for all the preceding Q's in my capital Q matrix. Okay? So I'm doing the dot product here. Okay? And for every one of them, what I'm going to do, I'm going to update my vector V, such that V ends up to be orthogonal to all of the precedings. Okay? So as we said in the slide, I'm kind of projecting V on all the previous vectors. So I'm making sure it's going to be orthogonal to all of them. I'm taking the norm of it in H, is going to be in the SN matrix, and I'm dividing by the norm to finally realize that I generated this orthogonal and unit vector V or Q vector. You get my point, Mohammed?
Yes, thank you.
Okay, so that was the main idea about Arnoldi's iteration. Now I'll go back, I'll switch back to the last slide in our presentation today, which is about, well, formally speaking, what's going on. So formally speaking, Shabab, this is what's going on. Sometimes we don't need only to see algorithms to see what is going on mathematically. So what we end up with in matrix language is this. So you are trying to estimate what? The largest eigenvalue and eigenvector for A. So basically you end up at the end with this. So A times QK, after iteration with QK plus 1 times the Essenberg matrix. Okay? And if you do a small computation, if you multiply by QKT, don't forget that the Q vectors here are orthogonal. So this is an orthogonal matrix. So if you multiply here, what you're going to have is this. QK times QK transpose times QK. So this is itself R. So it means that at the end, QKT times A times QK is an Essenberg matrix. Now I'm going to ask you a question. And whoever is going to answer me is going to get a bonus. Does it remind you of something here? Does it remind you of something you've seen before?
Spectral
Did you see one? Exactly. Firas, you deserve a bonus. So you see now, you've just shown that the Essenberg matrix is written using the spectral theorem. Okay? A, don't forget, A is your own data matrix, which is very large. And you've just shown that the way the Arnoldi iteration works is that, well, the A will be at the center of the spectral factorization of the Essenberg matrix. So the square matrix HK, in fact, would lose, in fact, the last row. It would be square. And why we call it Essenberg? Because it's an upper triangular matrix plus one subdiagonal containing H21 to HKK plus 1. And in fact, matrices with only 1, 0 subdiagonal are called Essenberg matrices. This is just for definition of Essenberg matrix. In fact, this means, in fact, because of the spectral writing, that the Essenberg matrix is the projection of A, in fact, onto the Krylov space. That's why what Firas is saying is important. Because here, HK is equal to QKT times A times QK. What you just did is a projection of A onto this reduced dimension subspace. So suppose you have 1 million by 1 million matrix A, and you want to work on a 100 by 100 dimension space. You get my point? This multiplication produces this projection. Get it, guys? Okay? Type. I'm not forgetting you, Firas. You deserve a bonus. So, just to summarize now what we did, the Arnoldi process to find HK is one of the greatest algorithms fact in numerical algebra. It is numerically stable, and the Q's are orthonormal, but it breaks down when, as we said in the pseudocode, in the writing of the Python code, it breaks down when the QK, its norm is equal to 0. This is where we inserted the absolute. In fact, this happened when the minimal polynomial of A is of degree K. So in most applications, in fact, this doesn't happen of the Arnoldi iteration, including eigenvalue next, the algorithm converges, in fact. And we'll see next time how to talk about the GMRS algorithm. If we go all the way to K, in fact, more interpretation, size A, then we have an Essenberg matrix, which is approximated by this Q minus 1 AK, which is similar to A and has exactly the same eigenvalues, which means that if you want to run this algorithm with a large number of iterations, well, you are going to share exactly the same eigenvalues then. And since H is an Essenberg matrix, it is easier to compute the eigenvalues of H than working directly on it, because you did the projection. So basically, what he is saying, you project A onto a Krylov subspace, and instead of working on the computation of the eigenvalues of A, work on the computation of the eigenvalues of H. And life is beautiful. Okay? So thank you very much, guys, for listening. I'll see you on Sunday. Don't forget you have homework to finish. And have a good weekend. Any question is welcome. I'll stop recording. Yes, go ahead.